Hi, we're Group 20. Our team consists of George Gabrit, Zach Weisenthal, and Madhu Govindaraju. For our project, we used reinforcement learning to solve a maze in Malmo, Minecraft. To start off, we had 3 goals that we set to be our milestones. The first was an easy goal, to solve a simple maze in 60 seconds. You can see the simple maze to the right. We wanted to be able to successfully use a simple tabular queue learning agent that uses discrete action spaces and complete the maze in 60 seconds. The next milestone was solving a larger, more complicated maze in 2 minutes. The maze displayed on the left has higher and more barriers. We wanted to use an agent with discrete action spaces and run DQN, A3C, or SAC learning algorithms and be able to successfully complete the maze in 2 minutes. Our final goal was a hard goal of perceiving and fighting monsters whilst solving the maze, as you can see on the right, in 3 minutes. We hope to have the agent take in a continuous action space and run DQN, A3C, or SAC learning algorithms and successfully complete the maze in 3 minutes.
Tabular queue learner.
Tabular queue is a reinforcement learning algorithm that we used, and it uses a queue table, which is a nested dictionary where each state has multiple actions and the state action pair has a reward associated with them. The agent gets a small negative reward for each step it takes and a large positive reward when it reaches the end of the maze. This way it's incentivized to take fewer steps because each step gives it a negative reward, and it's also incentivized to reach the end of the maze because it gets a large positive reward if it does that. To find the next move, the agent looks up the current state and finds the highest rewarding action to take and then takes that action. However, there's also a small chance to take a random move based on an epsilon. The agent runs many times and ends each episode after a time limit or it reaches the end. For implementation and hyperparameters for tabular queue, in the first milestone, we didn't use any heuristics. It was just -1 reward per step and plus 100 when it reaches the end. Tabular queue was able to find a great solution with haste. We had a small epsilon of 0.01, so it didn't improve significantly after it found a way to reach the end, because it would only take a random move 1% of the time. For the second milestone, more complexity was required, so we added a heuristic to the reward, since the maze was almost twice as long and had walls, so it was a lot more difficult to solve. The heuristic we used involved the X position of the agent and the X position of the redstone block at the end of the maze, and we simply subtracted the difference between the end and the current position from the reward. So if you're far away, you get a high negative reward, and if you're close, you get a very small negative reward. For the experiments, in our simple maze, we have a discrete action space with just 4 actions, and this yielded great results quickly. It was able to find a solution in only a few minutes, since the maze was so simple. For the complex maze, our secondary goal, we were able to get decent results, and it was able to solve the maze regularly towards the end. It took several more iterations to solve, but it was eventually able to solve it. And while simple, tabular queue proved to be a great algorithm for finding a solution quickly.
Gym ENV and RLLab. RLlib and AI Gym. Early experimentation. We began the quarter by experimenting with Malmo's provided tutorials and implementing tabular queue. We were eager to switch over to RLlib for its advantages in parallel training of agents and the plethora of reinforcement learning algorithms it offers, such as DQN, Soft Actor Critic, and especially A3C. In order to utilize RLlib, we needed to implement a wrapper for Malmo that inherited from the Gym ENV base class. Issues faced and the changes made. Issues with AI Gym. Getting a working Gym ENV wrapper for Malmo cost us much valuable time. but fortunately we were able to implement it in the long run. After several attempts, we discovered a wrapper named Minecraft Jim that took some alteration but ultimately was able to properly wrap Malmo. Problems working with RLib. After several weeks and countless issues faced while attempting to utilize RLib with our wrapper, we were able to get RLib training. We soon discovered that none of our machines were able to handle the high memory costs that RLib demanded when training our agents, so we were forced to resort to other means to train our agents. A3C Learner. What is A3C and how does it work? Asynchronous Advantage Actor Critic consists of multiple independent on-policy agents. Each agent carries its own weight and policy and interacts with its own copy of the environment in parallel. So you basically have multiple worker agents all running in parallel and training, and when an agent finds an improvement to the policy, it updates to the global network. Instead of learning Q values, the agents learn advantage values. Agents cumulatively update a global network, resulting in faster, more efficient training. Implementation and hyperparameters. With the help of some online resources and tutorials, we were able to implement a working A3C agent, which we trained on our maze. This agent features both a long short-term memory policy and a feed-forward policy, either of which can be used based on the application. For our agent, we focus more on the long short-term memory policy. Due to its strengths in video processing and memory/recollection, it is a lot more advantageous to use it for video processing as opposed to image processing because it can recognize recurrences in previous frames. For our hyperparameters, we experimented with many values but ultimately settled on a convolutional neural network and the following values: a gamma of 0.99, a rho of 0.99, an epsilon of 0.02, and an async update interval of 5. Experiments. We conducted discrete action space simple maze experiments on the A3C, which yielded great results rather quickly, but was often unpredictable. Continuous action space simple maze, the agent appeared to have been overwhelmed at times and spun in circles quite a bit. For the discrete action space on a complex maze, it yielded decent results and was able to reach the goal fairly regularly towards the end. Continuous action space, complex maze. Similarly to the simple maze, the agent spun around a lot and seemed quite lost.
Our results for our project.
The first video shows our simple maze for milestone 1. Our tabular queue agent is able to get through it pretty quickly, and once it's solved it once, it is able to solve it over and over in the same exact way. It doesn't go the most efficient way, it just hugs the left wall, and it doesn't adapt much because our epsilon is very small. The second video also uses the tabular queue agent, but it has the heuristic to move in the X direction more. It is able to reach the end, but it doesn't find the shortest path like in the first maze, and it follows the very similar pattern after it solved it once. As you can see again, it gets stuck kind of on the third wall and moves back and forth a little bit instead of just going straight to the end. For the tabular queue rewards, we have 100 episodes, and the reward range is from negative 3,500 to positive 280-ish. It starts out for the first 33 iterations of failing consistently. It doesn't reach the end, it has a very high negative reward, since the reward uses the distance from the end goal in the X direction. At episode 34, we're able to reach the end, and after that, there's a lot of progress. It stumbles a little bit, but by episode 55, it's able to consistently reach the end of the maze and does not have much modifications from there.
And here we have the A3C rewards graph that shows the average rewards per episode over time. As we can see, at first, the agent does not do so well. They get stuck in the first room, they're spinning around a lot, and their reward is not very high. As time goes on, however, we can see that the agent learns quite quickly and soon is able to consistently get a high score without memorizing the current maze.
What we accomplished was we were able to successfully apply tabular Q to a Malmo agent. We thoroughly utilized A3C to make an agent that was capable of turning and attacking with image processing. We solved all three of our mazes of increasing complexity, one small, one medium, and one of hard complexity. And we became acquainted with RLlib and GIM to be able to use in future projects.
That's all we've got. Thank you for this amazing quarter, and thank you very much for your time.